Hello, everyone. Thanks for joining once more the robotics seminar. I'm happy to introduce Katerina Fragkiadaki, coming from Carnegie Mellon University, where she's an assistant professor at the machine learning department. And before that, she got the PhD at UPenn, postdoc at Berkeley, and then I spent a year at Google Research right before starting at CMU. And in her research, Katerina studies algorithms at the intersection of computer vision and physical common sense, so to speak, to get computer vision to be able to appreciate the nuances of perceiving the physicality of real objects in real environments, like, for example, reasoning about properties like permanence, size, pose, affordances, and their variations of, different types of challenges in the visual field, like occlusions, for example. And at work for which Katerina has received many awards, NSF, Air Force, DARPA, Google, TRI, Amazon, Sony, you name a faculty research award, and it's listed in Katerina's CV. So Katerina, thanks for making time for coming here in person. It's great to be able to interact. And if I can say one more thing before giving you the stage, I realized the other day while looking in your website that you have one of the coolest and I would say more concise one-liners describing your futuristic goal for your research. And I think it captures really well. It says, and I'm reading from the website, to build a machine that would want to watch Ingmar Bergman over this. And at this, if you click, it brings you to the Keeping Up with the Kardashians. I just checked, I did a quick check in IMDb, and one is ranked at 8.2 over 10, and the other one is ranked at 2.8 over 10. I'll let you guess which one is which one. But I think that it's a great way to put the kind of thing that we would want one day for machines to be able to do, right? To appreciate the real meaning content that is behind video. So, Katerina, thanks again for coming. And it's great to have you here. Please take the stage.
Yeah, thank you very much. It's a great pleasure. I really had a wonderful time so far. Thank you to those that had the time to meet with me. I really had a wonderful interaction so far. Yeah, I'm very excited to talk to you about what we're doing in my lab. Please feel free anytime to stop for questions. So my background is visual perception. So as such, I see everything as a problem of visual perception, like language grounding, robot control, and so on. I think that everything will go away if we find the right visual representations. But we see language and control and action as a way to supervise, as well as also to tell us and inform us what visual representations we want to deliver, essentially. And here is a slide that I like from Bruno Olshausen. He says, is this the goal of perception? Is the goal of perception to take an image and to label the visible pixels in terms of embeddings, pose-aware embeddings, bounding box, and so on and so forth? And in the vision field, for many years, we were very much focused on feed-forward architectures that would take images and spit out labels. And even from the last 5 years, Bruno has been advocating that perception is not about feed-forward labeling. It's not about what you see. It's actually a lot about what you cannot see. Because there is a 3D world behind the image, and during the camera projection, a lot of things are lost, and you just see a 2D, visual observations that are very noisy and very incomplete. And somehow the brain can complete them very well, predict what can happen, predict what's behind occlusions, reason about physics and interactions, and this is what we want also the neural networks to do. So going from 2D to 3D is one way, but 3D is not the only hidden factor. Physics is also hidden, forces, and so on and so forth, so that we like our representations to capture. So decades now, people have been working on SLAM. SLAM can also be thought as a way of going from 2D videos to 3D representations. And here I'm showing a result from ORB-SLAM 2. ORB-SLAM 2 is already very old. Now there is ORB-SLAM 3. There is deep learning very heavy lifted droid SLAM, excellent work from ICCV 2021. And SLAM also takes a 2D video and gives you a point cloud of a scene and a camera trajectory. So it disentangles essentially the video observations into a camera trajectory and a 3D point cloud map. And in this 3D point cloud map, there is object permanence. So even I showed here a little teddy bear. So it is on the point cloud map. It was not in all different frames, right? So it does deliver, as we say, persistent representations. Now it works only on static environments. That's one thing. But the other main thing is that what it does, SLAM cannot do a model completion. It cannot imagine anything, which means what? Even if I go to 1,000 times to different offices and do my SLAM and build my maps and so on, next time that I will go in an office scene, very similar to what I've been before, I still need to go and look around to build that map. I cannot learn to go from 2D to complete scene representations. I cannot understand what's behind the computer screen, that objects have 3D shape, and so on and so forth. So the question where learning representations are trying to do is to go from 2D observations to complete 3D representations. And there has been many excellent works recently. For example, one revolution that happened recently on 3D perception is instead of using point clouds or instead of using voxel grids that suffer from discretization problems, you have implicit functions. Implicit functions is a function that you give it an x, y, z location, and the function spits out for you 0 or 1, occupied or not occupied. And in this way, you can have what they call infinite spatial resolution 3D representation. So we managed to handle the essentially the memory issues of 3D in this way. But what is the problem still? What is the problem still? The problem is that to build those representations, you rely on good detectors and segmentors. So you need to build one such implicit 3D representation per whole scene or one per object. And somebody else needs to solve the problem of detecting the objects or segmenting and so on. And another confusing part is the fact that there are two fields here. The graphics field that cares about rendering beautiful images, photorealistic, that can really fool the user, whether it's real or graphics rendered reality. And there is the computer vision field that what it cares is to understand the image. But as we saw earlier, understanding an image means being able to infer the latent state and re-render it. So here, the better renderers we built, hopefully the better we're going to do in the encoding process, going from the image to the latent state by rendering and repeating and so on and so forth. So the question is, how do we build those latent advances, essentially on 3D modeling and all these nice decoders, into the encoding process of going from the image to essentially that representation? The conclusion of this talk is that it doesn't matter that much what is your representation, whether it's going to be implicit or it's going to be explicit or voxel and so on, but it needs to be modular. Because if it's not modular, it cannot be reused. You cannot generalize. You cannot start building implicit functions of whole scenes because you're going to build it for this scene, and as soon as somebody moves, this implicit function is not going to be useful. If we change some chairs, again, it's not going to be useful. But if you build implicit models of every little chair and each one of you and your mask and glasses, you can remove the mask, you can move the glasses, and still I'll be able to encode and decode and explain what I'm seeing. Okay, so modularity is very important. So when we started working on 3D representations, we were trying to think, okay, what should our 3D be and so on. So back then we were very inspired by Rod, who in 1991 said that internal world models, which are complete representation of the external environment, they're both impossible to obtain, but also are not at all necessary for agents to move around and so on. Now, having said that, the Roomba robot does build an excellent map of the environment, and it allows it to clean. So he was advocating, okay, we don't need complete models, but in practice, the embodied agents have benefited tremendously for building better maps and solving the pose estimation problem and so on. So by looking at this, at his paper of this 1991, our conclusion was the following. What if we try to go from a 2D image, not to a 3D occupancy grid or not to a 3D point cloud, but rather to some 3D featurization, to some 3D features. Back then, there were no implicit, or at least we had not got aware of implicit functions, so these features would live on a 3D grid, little x, y, and z. And then from these features can be trained end-to-end from your final task. And your final task can be to detect objects, to predict how they're going to move, to track the objects, to predict actions, which behavior to select, and so on. So with C3D, not the output of the system, of the perception system, but rather as the inductive bias, the bottleneck in the heart, that could be trained end-to-end for a final task. And essentially, this talk is about discussing those 3D feature representations that started being explicit, living on a 3D grid, and how do we make them explicit? What is the benefit of those 3D bottlenecks over 2D bottlenecks and so on? And how can we use them for, intuitive physics, skill selection, and language grounding? So what we did, we were very inspired by SLAM architectures. We wanted to have a video as input and build a 3D featurization of the scene. So we did something very straightforward. Essentially, we made a network, which we call geometry-aware network, that solves the SLAM in its heart. So it has a three-dimensional hidden state, a 3D grid of features, essentially, exact what I told you. And also, when it updates its features with every frame, it estimates ego motion, much like SLAM updates the point cloud map. So here you see a video of a scene where there is a coffee machine. And then the first thing you do is you go from a 2D image to you shoot rays and you instantiate some shell, actually, of color pixels. And then you do 3D convolutions here on this 3D space. And then you instantiate some 3D feature map. And when the next frame comes, you do exactly the same process. And now you need to infer the 3D rotation and translation of the camera. So you estimate that. And you undo it before you're fusing the features. So first you undo the camera to stabilize. And then you dump the features in the 3D feature map. And the way to dump them is either you can average them, or you can put your GRUs and LSTMs. But all these GRUs and LSTMs will operate on already ego-stabilized features. And again, the same thing and so on. So now we managed to go from a 2D video to a 3D feature map. And the whole point of this process is that this is a yellow dot on a point, on a handle of this coffee machine. And after the stabilization process, despite the fact that the handle moves because the camera is moving, in the 3D latent map, all information about that point is at the same place. Okay? So this is stable. So the map is stable. No matter how the camera moves, the features are stable. While if you see the same thing with the 2D RNN, if you take a video scene and then you featurize it, you put convolutions, and then you update the hidden state using conv-LSTMs and so on, you'll see that as the yellow dot changes location in the image, because convolutions cannot undo essentially the camera motion, you'll see information from the same point everywhere in your hidden state. So your hidden state is mostly determined about how the camera moves rather than how the scene looks like. Okay, so each time the camera moves differently, you have different hidden states. So you cannot easily generalize across different camera trajectories. Okay, so here we took away the camera completely by estimating explicit like SLAM. So now what are we going to do with this architecture? How we're going to train it? We want to train it for a model completion. I want a test time to be given a single image, and then to do this on projection and densify my 3D feature map by predicting also what's behind what I see. So I'll train this architecture with view prediction. I'll have a query viewpoint at training time and ask to the network, that's how things look from this viewpoint. And then the network will try to predict those by orienting its map, rendering it, okay, and then decoding an image and try to match its predicted image to the input image. And this is a very biological, plausible task, predicting views. You just move around the scene. You are self-supervised. You don't need anyone to give you annotations other than your viewpoint, how your camera is moving. And then you can train now this GRNN, this geometry-aware network. And once you train it, now the network can imagine, can go from a single image to a complete 3D feature map. Because if you render the 3D feature map, it should be able to give you images from alternative viewpoints. And view prediction is not the objective that we came up with. A view prediction is, many works have considered training their networks with view prediction is as a form of self-supervision. But the main contribution here is actually this 3D bottleneck. And here I'm going to show you how this gets you generalization. So consider our architecture and consider the architecture of GQN, Neural Scene Representation and Rendering, from DeepMind in 2018, where again, you take images as input, any go motion, and you feed them and fuse them into either 1D vector or 2D, and then you render again to generate views exactly the same way as us. And imagine that you train those architectures in scenes that I saw in the top, like only 2 objects. And then you test them on scenes with 4 objects. And this is something that we do want our neural architectures to handle. They should be able to generalize to a variable number of objects. So here I'm showing videos. I don't know if you cannot see because unfortunately I had a video that was showing how the neural network sees the scene from all the viewpoints. But you can also see from this single image that our network can see four objects, despite the fact that it was trained only with 2. But the other network still sees only 2 objects. So this shows that, yes, you can grab an architecture and you can train it with an insane amount of data for view prediction, but there's no guarantee that you'll get any meaningful generalization. So the 3D space, the 3D bottleneck allows you to generalize. OK, so this is it. So that's the main idea. We want to go from 2D. You put a placeholder of a big 3D scene, so you allow the network to imagine whatever is missing in the 3D bottleneck. Now, do humans build 3D metric scenes of the environment? Absolutely not. We do imagine, but clearly not in a joint metric space. I mean, there's no way we can do that because in any case, we process glimpses, tiny little glimpses that we put together. So clearly, the 3D inferences of them don't need to be coordinated. But in any case, here we have 3D feature maps. Now, an important limitation from what I showed earlier is that we're predicting images. And predicting images is hard because there's a lot of stochasticity. Who knows how things are going to look like from different viewpoints? So instead of rendering images, here we ended up rendering 2D feature maps. So instead of asking you, give me the RGB values, I'm asking you, give me some width by height by 64. And so this is my top-down pathway that, given the input, tries to imagine how things are going to look from the different viewpoint. And jointly, I'm also training this 2D CNN that takes the query image and featureizes it. And then I have a pixel-wise contrastive loss that says the corresponding pixels better be close in embedding distance and far away. The non-corresponding ones should be far away. So you can do this either in 2D once you render or in 3D. So you can take the query view and lift it in a 3D feature map and say the 3D feature map that I imagined and what is actual there better match in a contrastive manner. And contrastive cost functions are extremely, extremely popular right now. OK, so back when we did it, it was just starting to become popular. So how things are looking like? So you have 2 views. And for example, Russ's work uses triangulation to train visual feature representations. So how this is different here? You have 2 views. And because you have triangulation, you know where every 3D physical point is going to render. And you can ask the 2 projections to have similar features. Where here, instead of operating on the 2D views, you lift the views into 3D feature grids, and then you match the corresponding 3D feature grids. So you can compare even things that are not visible in your images. Things that are visible in one view and not in the other view. Or even things that are not visible in any of the 2 views, and you try to coordinate them. So you do the contrastive matching essentially in an imagination space. And what you end up learning, and here I'm showing a slice of that 3D feature map from a bird view because you can visualize from any viewpoint, is features that correlate with things in the 2D image. Here you see lanes, for example, that usually we don't label. You see the lanes of the roads and so on. And you can use the same representations for tracking objects without ever using any tracking labels. You can track objects in 3D in this way, just by using visual 3D feature representations by view prediction. Now, what else can you do with those 3D feature maps? You should be able to do anything that you can do with the 2D feature maps. For example, detecting objects. And here you can give me some annotated 3D bounding boxes, and I should be able to train my system end-to-end to generate those boxes. And what we found is that indeed pre-training with view prediction will allow you to do well with less number of training examples. So here I'm varying the number of labeled data. And as you see, the red curve is the contrastive view prediction. And it has higher mean AP than training from scratch or training from RGB image prediction. So looking around is a useful self-supervised task to generate a model 3D feature representations for detection. So now, one big problem we had those representations is exactly the spatial resolution, what I mentioned in the beginning, because each one of those grid cells needs to be really fat. Otherwise, it doesn't fit in the GPU memory. So instead of having a 3D feature map, we'll have a grid of 3D implicit functions. So each one of those MIJK, each one of those feature vectors will instantiate one implicit function, okay? And so it will parameterize essentially a function. It has, each of those functions has some parameters and has this embedding vector from our 3D feature map. And this function takes an XYZ, essentially a displacement of a point from the center of the voxel, and spits out occupancy as well as the feature vector. Now, of course, the baseline for that is trilinear interpolation. You have your features at your grid location, and you want to estimate features outside of the centroids. Of course, you can do trilinear interpolation, but training implicit functions essentially gets you much, much, much higher, accuracy on your feature vectors, and I'll show you what I mean. Other than that, nothing changes. It's just that right now you're sampling locations and you're getting the corresponding feature vectors. And as you can see, 3D point contrast would be the baseline for this feature learning that we said, that you train features with triangulation. And you see that by using A-modal maps as opposed to only point clouds that are visible points, you do 5%, 6% better, okay? And you do much, much better than previous works that was not using implicit functions because our resolution essentially was killing the model. This is the 3D Vox contrast, our previous work. And then the 2.5D dense objectness is another baseline. So this type of doing feature contrastive learning essentially does much better when you jump in 3D and try to complete through imagination, essentially in view prediction. And VOTNet was a state-of-the-art 3D detector, and instead of just taking your point cloud and supervised data and train and detect objects, if you do view prediction, view contrastive prediction as pre-training, you have a huge gap in performance. All right, so this is what I wanted to tell you. And you have here a lot of shapes as well, and continuous shapes coming out of those implicit functions. These are applied object-centric. They're not applied in 3D scenes. But you can apply them either in object-centric images or in scene-centric images. OK, so this is essentially a description of our geometry-aware neural networks. And unless, are there any questions? Yes?
The orientation prediction, is it from some sort of estimation of the camera motion, or is it purely from the scene?
No, we estimate the camera motion.
So if you had a symmetric bowl, and no book that break the symmetry or something like this, would it be able to learn sort of the view-specific coordinates of that bowl, or is it, how would it deal with some sort of symmetry like that?
Right. So each one of these features looks a little bit at the context. So it would say that, yeah, this point of the ball should better match the one that I predicted as opposed to the one that is to the right or to the left. To the right will be closer to the boundary of the ball, so it would be different featurized than the center of the ball, let's say, right? Because every point is a function of the company. It has, same as every word is a function of the company. It has the same weight with their pixels.
Put the ball now in the new scene, and you were trying to do your reconstruction where you had multiple balls or whatever. How does that canonical coordinates match with your generalization across multiple instances?
Yeah, great question. Great question. So the whole question is, the main question we need to answer is those implicit functions. How do we assign them in the scene? Here we just assign them on a regular 3D grid, independent of the semantics of the scene. And you do expect that the convolutions somehow will generalize. And indeed they generalize. The 3D convolution, you didn't see it, but you trusted me that they generalize much better than things that collapse essentially the third dimension and stay in 2D. Now, how accurate will be your sphere models once you replicate them? Not that accurate. And this is exactly our ongoing work, which I'm going to show at the end of the talk, that these implicit functions should not be sitting on the regular 3D grid that is independent of the semantics of the scene. They better sit on entities, semantic entities of the scene. You're detecting balls and you are instantiating them. So in this way, you can have high fidelity and confidence that if you see a ball again, then again it's going to be featurized in a very similar way. Okay? Yeah, great question. So I just want to mention here, we have a Poolkit sitting in the room. And with Poolkit, we worked in 2016 on this problem, visual predictive models for playing billiards. So what we're trying to do in 2016 is, can we train a neural network that will learn to predict where balls move on a table. And we were very excited to see that the objects actually, infer the collisions, and they actually bounce on walls, and they bounce on one another. And we also put this into a model predictive framework and said, okay, now my goal is to put this, sphere in that particular hole, and what force I need to apply, and so on. So people have continued working on this problem, and here is a recent, I think, ICLR 2021 paper, learning long-term visual dynamics. And the general recipe is the following. We have an image, and the image is an image of a planar world, and we detect the objects, and then we featureize them, and then we feed them into a graph network to infer their interactions, and then we predict their future motion trajectories in 2D. Okay? And as you see here, the ground truth and the prediction are very accurate. They both predict that the ball is going to hit. Now, the important thing is that throughout all these years, the planar assumption has persisted. The world is still 2D. One thing that we were very stuck is when objects move, they all the time occlude one another, they hit one another, they change their appearance because of occlusions, essentially, and interactions. So if you try to infer physics in a 2D world, you need to handle this constant appearance and disappearance of objects. But in 3D, there is permanence. Objects just stay the same. Objects just stay the same. So what are we going to do then? Well, now we know how to go from 2D to a 3D feature space. So we're going to use those networks to do exactly this. So here is the visual input, and this is the GRNN that we just described. And now we're going to lift this scene into a 3D feature map, and we'll detect the objects. And then we'll, again, instantiate the graph network. But this time, the graph network will be in a 3D space. And the attributes of the objects will be their 3D locations, for example. And then this network will predict additive 3D rotation and 3D translation changes that you would use to unroll it forward and so on. So so even this play. But so the idea is that there is a 2D image, and the network imagines a 3D feature scene. And the important about this unrolling is that as you're pushing objects forward, these objects don't change shape, right? They don't change shape. They're rigid. We have ongoing work about deformations and about putting those graphs not on objects but on particle level. Okay? But here, these are object nodes. So let's see how this looks. Now you can have the same scene, and from seeing it from different viewpoints, and you can still predict very similar, object trajectories. All right? And here is another example. You have the 3D, and then you have your prediction. And then you can be dropping objects, you can be pushing objects, you can do anything you like with the objects and predict their interactions accurately without worrying about either occlusions or where is my viewing camera, basically. And this was in a Coral conference last year. And we call it the Viewpoint invariant object factorized environment simulators. And they try to capture physics in a very intuitive way through these graph network interactions. And you see that, there are two other competitors that you can do. One is forget about how objects look, just put X, Y, Z in their positions. And the other is take 2D patches of objects, exactly the baseline that I showed in the beginning. And using 3D features and doing the unrolling in a latent 3D space does much better. And again, you can embed this into a model predictive framework, and you have a cluttered scene, which you lift in 3D, you detect the objects, and then you know how objects move under interactions, and then you can, push the objects, plan a path where to push the objects, and so on. And you can this generalize in the real world because 3D is much easier. 3D detectors much easier to work. They exploit occupancy and so on. And you can move things in the desired locations, essentially. So skill selection. So are there any questions in our intuitive physics learning? Okay, so just to say that GRNNs were able to, go from 2D planar worlds to 3D worlds when they predict object interactions. So this work is related to many of discussions we had in the morning. How can we learn to act and manipulate a diverse set of objects under diverse sort of viewpoints? So this was our motivation here. How can we do that? Well, if we look at in the literature, we'll see two dominant approaches. The first approach will essentially discard appearance and will try to operate from the object state, where the objects are, where their locations, what is their poses, and usually this assumes that you have known object models, and then you infer actions. This is to the right. Now, unfortunately, this representation cannot generalize across objects by construction because it does not use the object appearance. Now, having said that, Pulkit and his students did show some reorientation policies that did not actually need to look at the appearance of the object. So yes, you can learn overly conservative policies that actually discard the shape and operate directly from positions. Now, the other paradigm is operate directly from images. But there are pros and cons here in these two representations. The first is data efficient but does not generalize across objects, and the second is data inefficient, but it has the ability to generalize. So what are we going to do? So our solution here was to again use 3D feature maps. You look at the object and you build those 3D feature descriptors for different parts of the object, that what is called these query visual features, that operate as queries for behavior selection. So you learn a mapping from 3D features of objects to behavior embeddings, and you have a behavioral library of different controllers that, for example, push the object in different ways, and these pushing controllers can be closed loop, and you learn them with reinforcement learning, or you can have a library of closed loop grasping controllers that you can hand engineer. And your reinforcement learning, the only thing that needs to worry is to learn this mapping from 3D features, appearance of objects to behaviors. And the pipeline is essentially in this, operates in this way. Again, we have an input image, which we lift in 3D and around the object. And then we use this as a query to retrieve the corresponding behavior. And this here, indexing operator is trained with reinforcement learning. Essentially, we have the robot applying different controllers of objects and seeing which features are compatible with which behaviors. Okay? And so things look like, so we apply this for grasping and for pushing. And so you have different behaviors. And you see that the robot is selecting the behavior that actually works for different objects. So here, for example, the second behavior grasps from the side. The hair behavior is grasping even, lower, and so on. And you can have your controllers. You have a gazillion set of controllers, engineered or non-engineered, learned or manually coded. And you can just learn this mapping function from visual features to the essentially behavior. And the important contribution here is that we found that your selector would operate much better if those visual features live in the 3D space as opposed to 2D space, because the 2D space is affected about how you place the camera. So here, you don't need at all to worry about how you're going to place the camera. We have here some baselines. So basically, you go to the real robot and you can place it anywhere, because this 3D feature representation will make a map where the ground plane, the table, essentially surface, is at the bottom of the 3D feature map. So VBA is the visually grounded library of behaviors, which is our work. Let's see here, this works. Yes, so this works, but it doesn't work smoothly. You see the video jumping from one frame to the other. Okay, well, it has, as you see here, has much better success rate than an abstract 3D that doesn't look at all at the shape or other, competitor representations. So we try for grasping and for pushing, and this is going to show up. This work is about to show up in Coral 2021. This work is in collaboration with Chris Atkinson, who is a big fan of libraries of behaviors, and that perception is there to tell you when to apply each behavior. And our contribution here is the 3D feature representations as opposed to 2D view-based representations for behavior selection. Are there any questions here? Yes.
Skill selection, so basically you just choose one behavior, or can you blend between behaviors as well?
Blend, no, but you can have multiple. For one specific object, you can have a whole distribution of behaviors that would work to pick it up or push it in a particular location.
But then you would have to train a policy for each and every behavior, so you cannot have infinite behaviors.
Yeah, we actually do that. We go in simulation and we train, because it's in simulation, tons of reinforcement learning pushing policies. Closed loop, by the way, these are closed loop policies. And then you have 30 of them, and then you leave them there and you allow them to be selected. And again, we do the same trick, actually, that I heard earlier, that when you train these RL policies, you can assume ground truth state, okay, which is very easy to get in simulation. But then at this time, you can look at the visual features essentially and operate from them. Okay, so the last part of the talk is how do we take those visual representations and map them to language to be able to instruct robots to, complete behaviors. So, for example, we want to be able to say, put the mug behind the keyboard, and then the policy will want to execute the actions. So previous works, a lot, or at least, one majority of previous work for instruction following could go from a language input and image input directly to a set of actions, okay? Now, the natural thing for a human to do is when you tell me something, even if I cannot do it, I'll be able to imagine what you're talking about. So if you tell me triple toe loop in ice skating, I really cannot do it, but I still can imagine what you're talking about and what will be the results in the environment. So we want to be able to give the same imagination ability to the robot. Then you require very, very, very little samples to actually execute the behavior. So what is this imagination? Imagination is generative networks that go from language and the descriptions of scenes to visual predictions of the scene. Okay, and this visual prediction, to tell you straight away, will happen in a 3D feature space, exactly what I told you earlier. We were very inspired by those linguists and neuroscientists, and from their conjecture about simulation semantics, that the way we understand language, the way the brain understands language, is by simulating the content of utterances using similar contrast to perception and control. So essentially, you have perceptual symbols that retain perceptual properties. For example, the size of the objects, or their color, or other attributes, how soft or hard they are. And language goes and indices those object models that you have, and also combines them and simulates them to generate the configuration. So, for example, from this paper, Symbol Grounding and Meaning, a comparison of high-dimensional and embodied theories of meaning from Glenberg and Robertson, this was written to explain to the people of that time that word frequency and word coherence is not the way to understand language. So back then, same as now, we had language models that would look at tons and tons of text and would say, okay, this sentence, I have seen this coherence of words before, I think it's very probable, or this sentence is improbable, is unaffordable. So these linguists essentially generate those sentences that are, as you see, are syntactically and grammatically identical. After wading barefoot in the lake, Eric used his shirt versus used his glasses to dry his feet. And we can very easily understand that he cannot have used his glasses, okay? So how can we get our language models, or language and visual models, to have similar inferences that we get when we read this language? Another thing is that people can answer gazillion questions about the situation. He used the newspaper to protect his phrase from the wind. So I can ask you, how many free hands the man had to do that when he was doing that? Or is the newspaper in front or behind him? Can this be single page and still protecting him from the wind? And is he holding the newspaper? Is he lying on top of the newspaper? Is the newspaper protecting from his net as well, and so on? So my goal here is to essentially try to hinge into the fact that language should not be indexing into logic, because logic is all about words, and words can never describe everything in the world. You cannot write a description in language that can exactly replicate how this guy is using the newspaper to protect his phrase on the world. You cannot just write on a set of facts and reason as logic reasons, all right? You have an image is 1,000 words, and from that image that you have and some picture, which this mental picture can be hopefully not very view dependent, you'll be able to ask you look at behind him now, and then you'll be able to imagine, you can able to infer all those facts. But you cannot shortcut directly to the facts without having the visual imagination. And the question is, how do we add this imagination to our models, essentially? And I'll show you how this connects to control, and how if you have those generative models that do goal imagination, you'll very easily learn policies that go from language to actions. Now, the important thing here is the following. This language is easier if it would index into some 3D configurations as opposed to 2D. Why is that? Well, I'll show you why. Because 3D, lots of physics inferences are very trivial. For example, things cannot interpenetrate in a 3D space. Or things are consistent across different viewpoints. Or things persist. With a view, if you render into 2D view-dependent image representations, you won't be able to do that reasoning process. The whole point is not just to index, but also to infer new elements. I'll show you in a little bit experiments where we show, for example, A is to the left of B, and B is to the left of C, and C is to the left of A. And then the model says, I'm not sure I can generate that. I don't think this describes a valid configuration. I tried to imagine it on my head, but it's impossible. Doing this with language model would be very difficult, or at least would be once you go outside of your training set. So let's see how we're going to do it here. We're going to use modular generative networks. And instead of considering images paired with descriptions, we're just going to consider scene pairs with descriptions. Because once you have a scene, then the agent can go around and can map the scene to a 3D feature map. And then that you have this 3D feature map and the parse tree of the utterance, then you can learn those generative networks. And these generative networks will be modular. They will generate the scene one object at a time. For example, here we have green rubber cylinder. This is the input and some latent, some random noise, and you spit out the 3D feature map of that object. And here you do the same for blue ball, and you spit the 3D feature map. And here is the spatial module that predicts how objects are arranged in the scene. And you feed it, for example, on the right of, and spits out the offset. And then you can generate a 3D imagination canvas. So this generative model should be able to say, okay, guy holding newspaper, so it will be able to generate the newspaper. What holding means, then in a modular way, dump the newspaper in the right place, and so on, and be able to reason. So the more we see and the more we learn about the world, the better our generative models are. Once you render the scene, should be able to agree with your 2D input images, of course. And as you see, we have multimodality. Cylinder can be anything, and sphere the same thing. And front left and to left behind can all you sample, and you see different instantiations because language cannot constrain what the visual world is. You have a lot of ways that A is to the left and so on from B. And so now that you train this with two objects, you should be able to generate very complicated scenes with many more objects by just imagining their appearance and dumping them in the 3D canvas. And the secret here is that as you generate the scene, you can reason about its plausibility. You're not going to add an object where there's another object already, because this violates 3D intersection, 3D non-intersection. And so here are different renders of the scenes that you have imagined. And So here, again, there was these videos that I showed you. In the last video, we had 6 mentioned objects, and the network by iterative sampling generator was able to place them in a consistent configuration. This is something that 2D models would be very difficult to do. And also, you can now generate to the robot, tell him any arbitrary long sentence about object rearrangement. Then the robot would imagine that rearrangement and will go and do it, as I'm going to show in 1 second. So here is actually the static image of that rearrangement on the bottom. So we are able to imagine different objects arranged on different special configurations. And we did exactly this affordability check, what we wanted to do in the beginning. We would give to the system affordable and unaffordable sentences, things that don't make any sense. And we want the system to predict whether this is possible or not by essentially trying to imagine the corresponding configuration. And we train a system to do this in 2D and in 3D with the same amount of data, and the 3D model was able to generalize better. Okay? And this also with 400 sentences. So aside of generation, of course, you need to do the traditional, very traditional and typical and well-established problem of referential grounding. You give me an image and a sentence, and I should be able to locate the objects that you're talking about in 3D. So you do, again, the same thing with modular detectors, where every little noun frames is mapped to an embedding vector, and the embedding vector essentially attends to a set of 3D object detections from the scene and does the pairing between noun phrases and corresponding objects. So if you have these two ingredients, imagination and detection, then now you can do instruction following. And the robot, you can tell to the robot, add a blue sphere to the rand of the green cube. So then the robot will say, okay, let me try to detect what you're talking about. I can find the green cube. Let me try to add the blue sphere. Here is a way where I could place it through imagination. And now I can essentially learn trajectory optimization policies. That would actually execute the placement. And this makes planning much, much easier because the heavy lifting is on that modular generative network that goes from language to the described configuration. Then the robot can just go and place every object in the corresponding location in simulation in the real world. So on current work, beyond put left to the right and so on, I mean, also in couple with transporter networks and so on, we put things in circles, or we put things in a line, or we put things in a line inside the plate, and so on. You can describe any, a lot of different configurations in this particular language domain of actions and rearrangements. And by having this decomposition in the middle, where language maps to visual scene configurations, and then, then the controls takes that imagined scene configuration and interprets it into actions, then you are able to do the thing. I had some question earlier, like when the action sequence matters. So in many cases, when you are, for example, to plate a salad, you also predict the corresponding order of the object. So now we're ready to close, and I want to discuss some ongoing work. So a lot of things that I described and a lot of manipulation happens on scenes where our 3D detectors and 2D detectors already work. You can go and pre-train them on ImageNet and throw tons of supervised data and share features and so on. Now the real world is way, way more complex. There are entangled configurations, there are things that occlude one another and so on. The question is, how do we handle perception under entanglement? I can take that picture and do our 3D feature map inference, whereby feeding it to that convolutional network, but it's not going to help my perception in any way. Okay, because I just don't have the annotations. Apart from that, the objects are so, interacting with one another that it's not going to help to separate them in any way. So some things that we've tried recently is what we call fast and slow generative models. So we train generative models of very, very basic shapes. For example, surfaces, or lines, or not lines, like cylinders, or very, very simple shapes, something like generalized cylinders. And we train to recognize them, encode them, and decode them. And then we take those sets of generative models and we throw them to some complex shape, like a table or an armchair that they've never seen before. And we allow the generative model to fine-tune and update its weights, and the encoder to try again and again, like essentially search through gradient descent, and you are able to decompose that complicated object into different shapes. So here is all the primitives that we use, for example, for 3D shape we have applied in those two data sets. And then we go and we give to the network an input that has never seen before, like a whole chair. It has only seen surfaces and essentially single legs and so on. And once you do a feed-forward pass, it does a really bad job. Our encoder essentially doesn't work because it is essentially applied to an input that it is very, very different than training time. You are really out of distribution here. Okay? You trained on primitives, you trained on single objects and single parts, and now you have a part composition. But then if you allow it to train and do gradient descent and allow it to search, you are able to see that how it's able to take a very complex shape and decompose it into primitives correctly. So we want to do the same thing with plating, where our primitives essentially are individual ingredients. And now whole plates come that are complex configurations, completely out of the training distribution, but through gradient descent and adaptation, essentially you're doing this game of analysis by synthesis. You try to see how your input image can map to your latent slot priors for the different modules of the visual scene, that if they are rendered, they were able to explain the image. And here we see we give very crappy inputs, partial point clouds, while the model had only been trained for complete point clouds. And while the fast prediction, the feed-forward prediction essentially is crap, which we expect to be crap, feed-forward models never work unless the input is within training distribution. The second, what we call slow prediction, that essentially is prediction through gradient descent, where we allow our model to adapt to every training example, is able to do the correct decomposition. This is very similar to planning versus reactive policy. So reactive policy, there's no thinking. You just look at the situation and you predict. This is the fast prediction. While planning, essentially, you try to search. You try to find the right way to get you to the right goal. This is what happens through slow prediction in these modular networks. And here's some other results. And here, again, some other results. And the important thing is to realize here that it has only been trained on very primitive shapes and exploits modularity to explain very, very complicated input configurations. So here is some preliminary results that we got from plating. We have these very complex images, but because we have access to videos that build essentially a plate, ingredient by ingredient, we learn these generative models through videos. We have this supervision from the arrow of time. And at the end, when you reach to the fifth, to the complete essentially plate, you can ask your generative model to generate a similar visual plan. And the images in the bottom are generated from our generative model, where it predicts the different objects and their location. And the important thing to pay attention here is the fact that the way it imagines crackers is as complete objects, right? So the primitives are complete. They are very entangled, they occlude one another, okay? But the priors that we have given to our generative model are complete crackers. We trained it by having access to tons of parts, isolated parts, and we let it to learn that distribution. And part of those distributions were complete crackers. So now you see those in occluded configurations, and you are able to infer, the segmentations and completions and the depth, let's say, ordering. So we believe that for perception to help control, we should be able to get those entangled scenes and parse them into the different, let's say, primitives, right? Then the robot will make its job so much easier. The visual plan is out. The only thing we need to is now have the sanction gripper go and place the objects in the right inferred configurations. So analysis by synthesis essentially is the, I'm so impressed that everybody now is looking at analysis by synthesis. I remember, 7 years ago, Josh Tannenbaum was talking about this, and it was way, way less, let's say, popular, okay? So now we are, as we said with Philip earlier, we live this revolution of generative modeling. And generative modeling is much more than what it used to be of, okay, take an image, squeeze it into a vector, decode the whole image, right? Modularity is important, disentanglement is important. How when you encode the shape and color and location different. And I do believe that this is going to be helpful for control. So our goal here is doing analysis by synthesis in video scenes, scaling up the priors, the shape priors, as well as scaling up the library of behaviors. And of course, scaling up the language grounding domain, as opposed to just put A to the left of B and so on. So thank you very much for inviting me, and it was a great pleasure to be with you. These are the students that worked on this. Fish Tang is actually my first graduate student, and she's a postdoc here with Josh. And these are the papers that I mentioned in the talk, if you want to take a look. Thank you very much. So let me know if you have any questions.
That was a great talk. Thank you. Who wants to take the first question? Come on.
Yes.
Vincent, wait.
Awesome, thank you so much. Fantastic talk. Also, the first time I saw a talk of yours in person, which is
Yeah, I'm glad to meet you also. You're Vincent.
Yes.
I did. Okay, great.
One thing that I find very interesting is that you investigate both generative modeling from the perspective of object-centric representations, where you have a single latent code per object, and at the same time with CocoaNets, for instance, you have these locally conditioned models. Where do you see that interface? Because these are to a degree kind of opposing viewpoints. You can either say the latent state, like the latent variables of my scene are object-centric, or you can see the latent variables of my scene are local. Or do you want to do both? Do you want to infer one from the other? What's your thoughts on that?
Great question. This is similar to Russ's question. Where do we put our representations? Do we put them on regular grids? Exactly like convolutions, right? Essentially, we replicate weights across or we make them semantic related. So the truth is the following: these images, these generative models, they had the backbone, the Dino backbone. Yeah. So Dino is just looks everywhere in attention and featurizes the image. So I really think that if we want to do modularity correctly, we need to build entity-centric representations. We can think of this as the problem of binding in neural networks. We should build representations that bind on entities in the scene. Convolutions don't bind. Convolutions is you give you a feature vector for a particular scene location, for example, in between the two chairs. We would never describe the scene in terms of, okay, there's a feature vector between the two chairs, right? Because there's nothing there. I think this routing of information essentially means that they're entities, and essentially they try to explain what the pixels show, and they attach and they try to group pixels to match them to prior models. I think the convolutions was a shortcut. The convolutional implicit grids was a shortcut to try to do something with 3D and model completion without going through entity decomposition, simply because we do not know how to do large-scale entity decomposition, but we know how to do large-scale convolutions and large-scale implicit grids. Do you see what I mean? Yeah. We don't know how to scale it up.
Yeah, makes perfect sense. So just to summarize what you're saying, so I understand it correctly, you're basically saying that at the end of the day, object-centric representation is the way to go.
Yeah, I wouldn't call it object-centric, I would call it entity-centric. For example, you're holding now the mic, I see a white label and this, and then the red and the black thing you're holding. So, I see all L entities. I can totally collapse them because I don't care now to, decompose them. But anything that is relevant for my task, I would decompose it, let's say, because the more you decompose, the more reusable are your, let's say, components. Yeah.
Cool, thank you.
Yeah, now having said that, I want to say that DALL-E is insanely impressive and puts all the featurization. There's no binding in the architecture whatsoever, and you can tell it language and can generate what you're talking to it about. And very often, what is to tell him makes sense. Now, there is not what it generates makes sense. Now, there is not much guarantee what's going to happen and whether you stay in distribution or out of distribution. Do you see? Now, having said that, I do believe that there is system 1 and system 2. So the reasoning system potentially need to be object-centric and thinking and slow, and the fast one can be anything it wants because it's within distribution, right? Yeah.
Cool. Awesome. Thanks.
Yes, thank you, Katerina, for your great talk. Also related to Vincent's questions, like for clever-like environments, like you can do object detections and model them in 3D using graph neural network. But moving on to the real world, what you have shown on your slides, where if you chop those carrots into pieces and merge them together, is it even possible to have some entity or object-centric concept for describing the environments, or do we really need that kind of decomposition?
Yeah, great question. So first of all, number one, you and me, when we see the carrots, we can individuate them. I mean, usually we don't, we just look at the TV, but if you ask me to count the carrots, I will go and manage to do that. Do you agree? So whatever we can do, the neural net should be able to do. Because it may be that, the carrot fell on the floor, you need to pick it up, or there is some, spoiled carrot inside this mess and you need to really dig it out. Yes, I do believe that analysis by thesis will be able to go there, and you have a bunch of lentils or a bunch of carrots will be able to represent and reconstruct every single module of it. Now, whether we need it, no. You potentially can use it at training time to figure out, okay, what I really need to do to reason how deep shots should go and so on. Now, at test time, when you are a cooking robot and you're going to be fast, you potentially don't even care to individuate anything. You can just operate directly from grid-like feature vectors, if you like, right? Do you see? I mean, that's what I think. It seems that we're going in that direction. It seems that we can model everything in all the time smaller and smaller scale, basically.
Okay, I'll take a question. So you've shown quite a few examples where you sort of create generative models, explicit models that explain somehow the appearance of how we see a scene in a 2D image, maybe with some temporal components. But it seems to me that if you really want to explain a video, there might be more things that you would need to capture out of the objects. I don't know if you've thought or if you've done anything I don't know, masses, like friction, material properties. I don't know if you've done anything along those lines or.
Yes, this is an excellent question. We need to model the physics between those entities and how they interact. For example, there is excellent work from MIT about particle physics. Now we would know how to render objects into shapes. We potentially have their particles, so we may as well represent those interactions. Part of the inference and the decoding process should not be graphics, should not be like, okay, what is in front of what, let me reason about occlusions. The rendering process should also apply physics and forces that you infer to make sure that your inference is physically plausible, right? So even for the inference of a very static scene, you don't care to predict what's going to happen in the future, which is usually what we talk about when we talk about intuitive physics. Even for the representation of a single static scene, you should be able, during decoding time, to inject your graph-based particle or object or slot or entity interactions. Yes, I think this is very important. We haven't done it, but it is the right thing to do. And with us, we had similar discussion. Absolutely, yes.
Do you think that that's like adding extra features in the 3D vectorized representation of the scene, or there's something else associated with it, or?
I mean, absolutely. So first of all, every feature representation should be able to index in the set of object files outside of the image. Maybe you will see the gift that your mom bought you in your 20th birthday, right? So this information is there, and by looking at your object, you should be able to index on any information you like, depending on the task and what to do next. Math and physics is something that is much closer to even the perception, the basic perception of the entities, that during analysis by synthesis, you should inject physics, basically. So analysis by synthesis is not about geometry. It's about geometry and physics of the entities. And physics is mass and interactions and collisions and yes, touch, what things touch, gravity, and so on.
Cool, thank you. Anyone else? All right. Well, thank you, Katerina. I'm sure that
Great, thank you.
she'll be happy to answer more questions after this.
Sure.
Thank you.